let's start with a quick reminder of what we did last time. We started analyzing the symmetry of an object called the stiffness tensor, Kijkl, that relates the strain, which is the gradient in the L direction of displacement in the K direction, to the stress, okay? And in particular, we stated that Kijkl must be equal to KKLij if energy conservation holds, that is to say, if the forces are conservative, okay? Then we said, if that is not the case, which is typical in a driven system, active matter, biological matter, then this is true. And this object can be split in an even part that satisfies the equality, plus an odd part in which when you flip these two indices, you pick up a minus sign in front, okay? You remember that. And in order to facilitate the understanding of this problem, we introduced, if you like, a geometric or graphical notation in which we decided to trade, and we said, oh, for simplicity, let's focus on two dimensions. Let's focus on a medium that is isotropic. And let's start seeing what are the moduli that are possible if we make, as a test case, a case in which linear momentum is conserved, which means that the forces will be derived as divergence of a stress. We said angular momentum need not to be conserved, and energy need not be conserved. Okay, and of course we can we can consider other cases, and we will momentarily. And then we derived pretty much from scratch that in addition to the bulk modulus and shear modulus, last time I might have used G, let's stick with mu if you don't mind, because I have the notes with that language. In addition to this one, that are essentially this response function that describe the resistance of the material to that deformation. There are also these two additional coefficients, K naught and A, that are the so-called odd coefficients, that are describing the amount of work that you can extract from this medium when you do a quasi-static strain of deformation. And there, for that reason, they're characteristic of media that are made out of batteries, okay? And towards the end, I mentioned, and then I clarified for the groups who are working on the problem that I've assigned, that if you did not want to think directly in the continuum, but you wanted an example of a microscopic force that would satisfy, that would lead upon coarse graining to this law of elasticity, then you have to think along these lines. If you have a force that is central, that is to say, the force is oriented along the direction of displacement of the two particles, no matter the form of that force, algebraically, you can always write it as a gradient of a potential, because it's a one-dimensional problem. So any part that is that you cannot write as a gradient of a potential must come from a response that is transverse. So the simplest generalization of the spring, which is, of course, assumes that you have a minimum of a potential, you linearize it around it, has two parts. This is just a Hookean spring. If this is a spring, you stretch it, say, there's a restoring force along the lines in which you're displaced. This is the central force because it's in the r at direction, where r at is this direction and phi hat is perpendicular to r at. And of course, you can decompose any force in those two axes. The phi hat direction also has its own little. And so this is, if you like, a linearized spring that as a component, this one here, that cannot be written as a gradient of potential. As a result, curl of F is different from 0. Okay, so if you had a medium made of such, with this type of interparticle forces, you coarse grained it, you would not only produce a bulk and a shear modulus, you would also produce these two, and they would be proportional to this object. Okay? If you like, this is the microscopic counterpart of that. Please notice the very strong similarities between this matrix and this one here. Okay? The entries here are 0 because we didn't want any rotation, rigid body rotation of the medium to result in forces. Similarly here, I can rotate my spring, okay, like that. And if I don't change the distance, I'm assuming that that doesn't generate forces. On the other hand, if I stretch it, I will generate a force both in the radial direction, that macroscopically will give rise to B, and one in the transverse direction, which will generate torques. And that is the origin of this microscopic coefficient A. Okay, Leo.
Well, so one is, it's a little strange that you, okay, so the lower block,
Yeah.
writing only into symmetric part. One, you could add the symmetric part.
In the lower block. If I do that, it's no longer, so this I didn't prove it in detail, isotropic.
Then
The top one is compatible with isotropy. It's compatible with isotropy. Yes, yeah.
but it's also straight, but
It's not purely antisymmetric. So this could be, yeah, this could be thought as an antisymmetric part plus a symmetric part.
why that choice? I guess it's because you want a 0 there.
Is because I wanted a 0 there. If you're okay with having a medium that when I do a rigid body rotation produces a pressure, such a medium, however, would not be a freestanding one. You see what I mean? Like if I put something on a substrate and it sticks to the substrate, interacts with the substrate, then if I rotate respect an axis, that can cause a response. If it's freestanding, I would naturally want that to be 0. But that, since this matrix does not have to be 0, and it can be whatever I want.
It's hard to have that intuition for the 0 once you abandon, once you think of it as active, and then it's hard to have that intuition that it has to be 0.
And you don't have to. The only thing you have to do is you have to ask, what are you trying to describe? So if an experimentalist says, I have a way to know, once it rotates, like a rigid body rotation, to guide you into having a pressure, which means that whatever interaction his body is made of must not depend only on the relative distance of the particle. Because if they depend only on the relative distance of the particle, and that is not changed, there's no reason why if they remain at rest, they will produce it. Like this thing, for example. That is the problem. But that question, these questions also entail asking a very legitimate question, which is, say something like this microscopically. How can it arise in an experiment? Okay. Now, this, of course, is one of the questions for you in the problem. But I want to show you an example of the paper where I've directed your attention to. This paper was published. This paper was published only very recently, but reports measurement of both of the elastic moduli, cannot and A. In particular, notice that the important dimensionless parameter here, microscopically, is Ka divided by K. This ratio controls the ratio between, for example, odd moduli to normal moduli. Okay? And so in this paper that I'm gonna show you, that I advise you to read after doing the little exercise to compare, is this, I think it's called living odd elasticity of living crystal, or some variants of that from the lab of Nikta Fakhri at MIT. They measured there, for example, odd elastic moduli that they report odd elastic moduli that are as large as 10 times the normal one. And I want to tell you a little bit about how they interpret the results, leaving you a few pieces to fit yourself in the homework. Before I do that, I want to do another little exercise so that we're on the same let's imagine that you come here and you say, oh, you know what? I have a medium, I have a solid that does not conserve energy, but conserves angular momentum. Please tell me what can I expect, since we are in the position of deciding that a priori. So let's look at it, okay? Remember, what was the condition on angular momentum conservation? It was a condition of sigma ij that we stated before. Anybody? Symmetric. The other thing that I want to draw your attention to, in order to, these guys, the yellow, they're this. They're this. These guys, they're this column vector. In order to pick this one here, we multiply by the tau matrix that was -1, 1. That is associated clearly with the antisymmetric part of the stress tensor. So if we want that part to be 0, it means that you can't pick up a non-zero component here. Agreed? That means that you can deform whatever the hell you want here. Should never pick up a finite one here. What's the condition for that to happen? Huh? Yeah. So this term would not be present, cannot be present, if your medium conserves angular momentum. Now, one thing you could say is that, well, but you just told us that if I have central forces, I will be conservative. So the only way of not being central first, and that's Stokes. Yeah, only if the forces are pairwise. Okay. Now, people think, well, all these airy details, but keeping in mind that all the forces that we're going to be talking about are generated by things moving in a complex medium, in particular hydrodynamic interaction, there's absolutely no guarantee that they have to be pairwise. In fact, there's almost a guarantee it will be non-pairwise, and the question is, how big is the non-pairwise part? This distinction is, how to say, conveniently ignored in the analysis of that paper, okay? And by almost everybody, including us. Okay, so let me show you what Nikta did. So Nikta, I guess has a good relationship with the embryos, and she nurtures them, puts them in water. She gave me a lot of details when I visited on, this guy, you have to feed them and stuff. But once you feed them, since they're alive, they do all sorts of things. And in particular, apparently they like to crystallize. Okay. And so these are her movies. Clearly, you see a bizarre object. I mean, you can't argue that this is well, now it's a fluid, but once you see the crystal droplet, if you want to call it that way, I don't know how to call it. There you go. There's clearly a triangular, an hexagonal lattice right there. And each of these guys, despite you cannot see it because the movie is so fast, has internal torques, is spinning. Why? Because these guys can swim, they're half essential. Okay? They do it by themselves. So within this platform, she said, okay, let's try to understand the behavior of this system as if it was a solid. What moduli would have. And of course, I mean, she was aware that these things could potentially exist. And measured it. And I'll tell you at least briefly how she measured it, and I'll show you by equations what the general idea is. Before doing that, I want to say the fact that this is leaving for the perspective of generating odd elasticity is just the fact that, say, a colloid, where it will not spin by itself. I mean, my colleague William Irwin, for example, has colloids that are Janus, let's say. Janus meaning they have an in-plane dipole, magnetic dipole. If you put an external magnetic field, and you rotate the magnetic field, it will drive each colloid. It's not quite the same because this can spin freely. There will be an axis, but it will give a rotation. It will move the water around and potentially can generate the same thing. And in fact, William has seen some effects that are consistent with the presence of these moduli, although he hasn't quite been able to measure them yet. So what is essentially in this system, let's try to understand, the mechanism, and you'll study it in more detail when you read the paper, that brings interaction of that form. This requires a little bit of hydrodynamics, meaning let's assume, and here is there's some early paper that's actually quite nice by Steve Granick, who studied this with colloids. And already they highlighted, following to a lot of work in classical fluid dynamics, that if you have two particles spinning in water, there is an interaction between them, mediated by the fluid in between, called the lubrication force, that is proportional to the speed at which they spin, times the logarithm of their distance with that form there. Of course, this is not a spring, but you can imagine if you linearize, you can bring something like this, or variant thereof, at least there is a transverse force. So this is what the experimentalists are attributing to the transverse force that upon coarse graining leads to this. Okay, that's in your field. Now, of course, what they argue is, if you look at the picture here, they're almost touching. And if you don't know any fluids, here's my intuition for you. I mean, maybe you don't know any fluid, but you know friction, at least. In elementary classes, we know friction. Actually, friction is a very difficult subject, but we presume that we know friction. And what I know, at least that I learned in school, is the following: friction. So friction idea is I press, so I'm pressing down. Then I try to move it transverse to the direction I press, and friction causes a force that is proportional to how much I press, but perpendicular to the direction I'm pressing. So friction is a transverse force. And in fact, you can generate these things also with granular media that are frictional. But the important point is that in order for this force to be there, there's somebody who has to push to make it slide. That's where the activity comes. So I ask you, please zoom in the area separating those two guys. And in fact, following Eric's comment, let's make them very, very close to each other. Here is, they're super close. These are the two circles. This spins like that. And wait, I want to spin the same way. Yeah, this spins like that. You see what I'm saying? But this guy is coming down. So if I zoom here, it's really two planes that are sliding past each other. And so that formula, this is my, how to say, hand-waving explanation of what is a crucial result of fluid dynamics. It's essentially friction. It's friction due by this layer of water that's in between. Okay? So nothing particularly exotic. The activity of the liveliness, the reason why these guys have to be fed, is that they have to spin. And that's why essentially William, at least potentially, can do the same thing with the spinning colloid. Okay? Now, I can't resist pointing out that there are phenomena in nature, although people don't seem to have registered this message, that, but you can read this review called Odd Elasticity and Odd Viscosity. If you take, for example, a pattern made in turbulence, the turbulence is some complicated phenomena powered by the equation of fluid dynamics. And actually, let's not talk about it like that. If you cook, sometimes you boil water. And when you boil water, there's stuff that, maybe if you throw stuff in that water, there's things that patterns that form on top of that thing that you're trying to cook. I mean, this doesn't sound very appetizing. But these patterns could just be like patterns in the water, like this. Now, this is an hexagon, but it's not an hexagon of particle connected by springs. It's just a pattern. You could ask, what are the rules of the dynamics of this pattern? This is also governed by odd elasticity, and more precisely by the equation of odd elastodynamics that we're going to derive. So how did Nikta measure the moduli in that system? She did it in two ways. And the claim in that paper is that they lead consistent result. One that I'll talk in detail, and the other one that I'll talk less in detail. So the one that I will not talk in detail is following a prediction done by Lara Braverman, who's in the audience here, with Colin Scheibner. What they did, Lara is at Harvard now, but was an undergraduate with us in Chicago. Colin was a PhD student with me, and then is in Princeton now. So what they did, the two of them, they studied, so in crystals like this, sometimes the number of neighbors is not always 6. There can be defects. anomaly in the coordination number. I don't know if anybody has talked in the summer school about defects. But if not, let me just say, they're called dislocations. They are like a 5 and a 7 next to each other. So these are places where the anomaly in the structure of the crystal creates a deformation, a strain around and a stress. The pattern that is created depends on the equation of elasticity that you have. So by measuring that pattern, you can extract whether these coefficients are 0 or not. That's one way you can. The second way you can measure moduli, I ask you, how do you measure moduli? Why is the speed of sound very high in steel and lower in a biological gel? Anybody? Now this, huh? I know that you know, but I mean, you've been in this damn school for 25 years. I mean, okay, right. Besides what you did before, right? Okay, no, but thanks to Leo. Yeah. Huh? Okay. Well, at least he's learning. I mean, so the speed of sound is generically given by the square root of the moduli. Okay. So usually studying the spectrum of the excitation in this medium will give you information about the moduli. However, typically this is done for these guys. So one question that we have to understand is that what type of waves exist in this medium? Okay, this is quite an interesting point that I want to now attack. Okay. Notice that we put asterisk to all of this. I haven't told you yet how the equation look like if I knock off also linear momentum conservation. And the reason why I haven't done it yet, why didn't I do it? Oh yeah, because it would entail analyzing not only the stress tensor, but additional contribution. We'll do that later. Okay. For now, let's try to understand in this medium, which is what Nikta allegedly has, how do we understand waves? Okay. So I thought that it was pedagogically interesting to do it two ways, the honest way and the dishonest way. With the dishonest way first. The dishonest way is scaling. Okay. And the dishonest way is scaling, yes. And the honest way is calculation. And we'll do both. Maybe before I do that, I want to show you one little thing. I've been saying it, but maybe I didn't prove it as much. Let me prove it. You see, we keep saying this fact that work is generated if I go around the loop. Now, it's intuitively obvious, at least to me, given that this medium is made of forces that have that form. And it would be even more obvious to you, given that you're asked to literally do in the homework a loop like, like you can do a loop like this. And you can prove that this spring will have a non-zero work proportional to Ka. But I want a formula. For example, okay, it's going to be proportional to Ka, but does it depend on how large the loop is and how? Okay. And also, you're going to prove it in your homework in the microscopic single spring thing. For gymnastic with mathematics, I want to show you first at the level of the continuum how you do that. Okay, using this geometric notation. And once we have that formula, we know how power is generated in this medium, and we can understand how the wave propagates. Okay, so let me do first one thing. So the formula for the work, and I'm going to do a line integral because I want to go around the loop. It's the moral equivalent of F dot dl for the single particle. Okay, it's just that now cast in terms of stress and strain, because these are the continuum counterpart of that. It will not surprise you perhaps too much, but I will not prove it with all the gory details, that the formula is you undergo a path in strain space, you multiply it by the stress, and this object integrated gives you the work. Okay? If odd elasticity was not there, this would be equal to 0, because work is a state function. Now, what I'm going to do is I'm going to rewrite this as in my what I claim is our simplified notation, which essentially amount to calling a global index Uij with one Greek letter. Okay? And now, just for simplicity, I say the following. How about don't even bother about this A coefficient? Let's consider a loop in strains in the space of shear. Okay, so we only have this subspace, which would be totally kosher, especially if this was 0. But you choose that. Okay, why? Because these matrices become 2 by 2 matrices, and it's perhaps a bit easier to do the algebra. Okay, so what do we do then there? The second thing I have to do is, this is a line integral, convert it into an area integral using, what's the name, Green's theorem. Okay, Green's area integral. Please notice, by area, I mean area in strain space, not area in physical space as it would be for this guy. Then Green's theorem, how do you call it? Curl of something. Okay, what's curl of something? In 2 dimensions, you take the antisymmetric tensor, epsilon ij. I forgot what it's called. No, it's not Levi-Cheat, it's the other guy. But like 0, 0, 0, 0, minus 1, 1. Okay? So I'll just write down the formula. I think you get it. This guy. Cool. Then you have to take this object and operate on it with a coordinate that is this. So you write down d sigma beta d mu alpha. Okay? Yeah? Now, this is the antisymmetric object. So now, if we focus on odd component. Why do I focus on odd component of the stiffness tensor? Because the even one will gonna give me 0. Understood? Yes? Good. That means that the sigma, the relationship sigma, what is it? Beta equal kappa beta alpha u alpha. This guy will be perfectly antisymmetric. Yes or no? Agreed? Huh? Cool. So if I take this and I take a derivative, kill this, left only with that object. That object has to be, we only care about the perfectly odd component. So this object is equal to epsilon alpha beta. Pure perfectly antisymmetric. Yeah? So this thing here can be rewritten as epsilon alpha beta times k naught dA equal, what is this guy? Do you remember? It's first of all, in order to make it matrix multiplication, flip alpha and beta, and then you have to multiply those 2 matrices. The product of those 2 matrices is minus delta, I believe. Okay, but there's another minus in front. So assuming that I didn't screw up the sign, you get 2k naught times area in strain space. So the 2, whatever, is 2. K naught we expected. Area in strain space seems pretty logical. Okay, is this clear? Is this clear? Question? No? I forgot to do one thing. So this is great. So now we know how work is generated, but we confirm that by going in loops, we pick up work, and the amount of work depends on the area in strain space times the odd elastic coefficient that couples the 2 components in which you do your loop. So if you did your loop not with 2 shears, but compression and rotation, which is what you will implicitly do microscopically in your homework, then the relevant would be A. You see that? Because this is the only odd one that's there.
The testing will depend on whether you go clockwise or clockwise.
Yeah. Curl. It's implicit in the curl. And another thing that I should have said, or perhaps I'll say now, is that the rotation, unlike that are constrained to be positive definite by stability, need not to be. Meaning that it can convince her friends to spin in the opposite direction, she flips the sign of K0 and A2. Okay? So that's how you can understand the transformational property of the object. Okay, what I forgot to do, but it's not a big deal, is just that you have to wait another minute. I didn't plan this for theatrical reasons, for me to show you the waves, because one thing I didn't show you is that there's not only stuff done with biology that is of this type, or with driven soft matter like this William and potentially even rotating Rayleigh Bernard. There's also robots. Okay, and I want to show you these robots for two reasons. These folks are responsible for this. These robots are a realization of a microscopic interaction that does not involve torques. So in this world, A would be 0. You see, some people have the misguided perception that all the elasticity requires microscopic rotation. This is not true. You can see from the fact that if I kill torques, I kill this. I don't kill this. However, that perception is not completely flawed, because notice that in this matrix here, there's a -1 and there's a 1. But I could have put a -1 here and a +1 there. So this medium, given that it has baked in an antisymmetric matrix, knows about chirality. So even when there are no physical rotation, there's still the sense of a loop that takes place in strain space. So some symmetries have to be broken, most notably parity. Okay. So I want to show you an example of how you make a medium where there's no torques, A is equal to 0, but this term still remains. As I mentioned before, the interaction must be non-pairwise. Okay? And this is a robotic realization done by my friend Corentin Coulet, and I believe a lot of the things that Itai does could be programmed to do this. The idea is very simple. This odd elasticity comes from these weird microscopic interactions that don't seem to entail restoration of a spring in the way you're used to. But the way you're used to is whatever you've seen up to now. But if Itai or Corentin goes in the lab and decide to program the interaction, it's a bit when I talk to you, like, we can talk and I say hi, you run away, you say hi, and I come and hug you, right? There's nothing wrong with it, because this is signaling. Two cells can do that. There's no reason why this has to be reciprocal. Do you agree with that? Right? I mean, it's totally reasonable. It's only reasonable to assume those properties when the interactions are perfectly physical. But these guys are programmed. So a more mundane example is this. Let's imagine that there is this, I would call it there's a technical name. I used to know these things. It's a linkage, two-bar linkage. Think of it as two pendula, okay? And imagine that there was a spring connecting that stick with that stick. Then you would have an intuition of what would happen if I push either on the left stick or on the right stick. It would be symmetric. Let's check out what happens here. I push this. Okay, this is as if there was a spring in between. Do you agree? Now I push on the other one. Comes in. This is an example of non-reciprocity. Why is it possible? Well, because Corentin is programmed like that. He can do whatever the hell he wants. I mean, and he can still legitimately ask, given this building block of my robot, I make a distributed robot with many, you're going to see it in a moment. Please tell me what is the emergent mechanics of that object, or the adaptive object. And we should be able to answer those questions with this mathematics, and we are. There are two things that he has to be able to program: sensors, but also actuators. Because I want to convince you that this interaction violates conservation of energy. And that's why it seems so strange to you. How do I see that? Well, let's write down the relationship between the two torques that you would experience. If there was just the two pendula, and there's a delta theta 1 and delta theta 2, you would have this diagonal part. But Corentin has engineered off-diagonal term with opposite sign. And that's why when I change delta theta 1, I have an effect of theta 2. and the opposite when I do the other way. Okay? Problem with this is that if I take the curl of that, it's a cousin of the one up there. Because of how it is constructed, it doesn't violate angular momentum, but it still violates conservation of energy. Is this clear? Okay. So now you can say, let's make objects out of it, and eventually crystals. So this is something I want to show you. Current arm goes in and switches off the motors. Now should be life as we know it, because it's effectively switching on K naught. Okay. So you touch it, doesn't do anything. Just goes back. There's a bit of friction or air, it dies. Let's switch on K naught. This is what happened. Keeps going. Keeps going on a side. Well, why? Because it's powered by this mathematics that you touch it, starts the cycle. The more it does the cycle in strain space, the more work he gains, and he can invest it to do another cycle and another cycle. Okay? So here is not a wave, it's a shape change, a continuous shape change that you're triggering. And of course, you can use this for functionalities. Okay. One thing that you can also show is that if you have those equations of motion, you see, this is the force. Now can you write down the equation of motion with inertial dynamics? Because these things are large. If you like, if you calculate the frequency, notice that the red part gives you growth. Why is that? Well, if you have a system that you keep pumping energy in, well, at some point it will blow up. Of course, if you make it on metal, you're not going to break the metal bars. But it will, you see what I'm saying? There's a runaway mode. We will return to all of these things and understand them mathematically in detail. The equivalent of what I just showed you here for this toy is the following. You can study the motion of that structure in two coordinates that are the shear deformations. And he keeps doing loops. And as he does loops, it generates work that is equal to the area here times K naught. And that can induce the next loop, even if there is dissipation. In fact, it can induce these things even if it's overdamped. Can you see that? The robot. A decentralized robot for that matter. And of course, it can have functionalities. You know, this is one of my most cheeky slides, the rediscovery of the wheel. Now, the normal wheel is a rigid object that rotates and attached to a shaft. The shaft moves the wheel. The wheel doesn't have to adapt to the terrain to move. It may adapt to the terrain if it's made of rubber to make you more comfortable, but it does not move more the more rugged the terrain is. This wheel, on the other hand, here is a terrain which is rugged. Can you see the terrain that is rugged? See the wheel? You first touch it a little bit, starts moving, goes up on the terrain, keeps climbing. No problem, because it makes, it can generate work. And the more it bounces, the more it deforms. The more it deforms, the more it can walk up. Notice there it should be stopping, but no, not happy, bounces back and forth. Because it cannot stop, right? So imagine if you wanted to do a rover and you deploy somewhere that is very, unreachable. This is a way of constructing a robot that is not centralized, a primitive one. Okay, and of course you can also imagine mechanism of this type to be a play in biorobotics or even biological systems that undergo adaptive locomotion. Okay, but you can also make a crystal like that. Okay, and now notice you take an object and you drop it. See what happens, and tell me if you can understand why. You see, it drops straight. Look how it bounces at an angle. And that angle is always to the side. Please look at this equation and tell me what sets that angle. A normal crystal cannot do that. If you drop something straight, it goes straight up. What sets the angle here? Who knows about the difference between left and right? This, the fact that I have a minus here and not here. You see what I'm saying? It's the fact that the medium we cannot has inherently something chiral in it, even if it's not made of spinning things. So in that sense, it's true that it's a chiral structure. except that I said that those microscopic building blocks are created to have no torques. So we know that that cannot exist. That cannot exist.
So all your examples like a 6.
Yeah.
Is there a reason?
This one, they built it like that. In 2-dimension, it's very hard to, when you try to colloids or anything in 2-dimension, unless particle is shaped, you tend to make an hexagonal lattice. But we can coarse grain any lattice geometry we want.
Just to be devil's advocate.
Yeah.
For whatever.
Yeah.
Like, you could program this thing to like jump and do flips and things.
Yeah.
And all kinds of other crazy stuff. And then you could say, well, now we're going to discover some new elastic coefficients, but it's really just programming.
No, that's the point. Can I interrupt you there? I'll comment right away on that. No, that's good. That's exactly the point. No, meaning that the design space is limited. Because if you tell me this object is 2-dimensional, you can start making all sorts of complicated structure in these distributed robots, but there's only this amount of entries in this matrix. And given your design choice at the beginning, I can tell you a priori what is allowed. So I can fill up this object, but this is my limit. So in that sense, yes, I can construct exotic, even more other exotic mechanisms. But the power of this is that it's a bookkeeping device that allows you to answer the following question. Given a choice of microscopic, robotic, or active building block, what can I expect without doing an experiment at the macroscopic level in terms of response?
I mean, I think it's because they're identical units that you're building your medium from.
That you can homogenize. Right. Yeah, that you can coarse grain it like that. But please notice one thing. This could have been disordered, and the disordered lattice is still isotropic. So my consideration based on symmetries hold irrespective of the ability to coarse grain the model or not. In this case, we can coarse grain it analytically because it is ordered.
Well, if it's statistically, homogeneous, yeah.
Then that's the answer.
You could just make right-hand side 1 plus. That's it.
Yeah.
Then it could be much.
That would be an inhomogeneous mean. Yes. Then what would happen is that those coefficients would be space dependent. But the point I think I was trying to, maybe I was too enthusiastic in interrupting you, apologies for that, is that you could ask the same question for colloids, for example. You could say, if you program colloids, you can have any moduli you want, the passive one. And if you make it anisotropic, there can be 20 of them. In a sense, what we're doing is the same exercise of telling you, given this enlarged design space that involves active component, how can we classify everything that is possible without you doing an experiment in advance? And I believe that that has some power.
But there's some assumptions of like you could send more power to the right part of your, so there'll be like a spike on one set of those guys. You're not including that. Like where all of a sudden there's some energy goes into the upper right unit, and that thing does something.
Oh, so what you're saying essentially a non-uniform response.
Like non-uniform,
Yeah.
Not steady state.
Absolutely. Absolutely. And in fact, structures like this can do it even by themselves by going unstable. Absolutely. Absolutely. But the point is that a lot of that can be understood from this equation. Because in fact, this is what we're going to be deriving, the stability domain. Okay. So with this, go ahead. Yeah. A lot. And keep in mind that this is already this big, so it's a demo really. I don't think that this is scalable with this specific technology. Yeah, it cannot. If you flip the cannot, it will go the opposite way. Okay, so what I want to show you now. Question, please. Yeah.
That particle that pops out, does it come up with?
Yeah, you can if you choose this coefficient to be sufficiently strong, it can bounce higher than it came down. Yeah, absolutely. because you don't have to conserve energy. I mean, I don't really know what the answer is with a number, but this is made of plastic and rubber. So I can't imagine it can hold more than a kilo. But you should ask Corentin if you want a precise number. Of course.
I would imagine this model.
Yeah. You don't even have to imagine because we're doing it on a computer. And for that, you would need something, ideally, something maybe non-cohesive, like that they can break the bond even without destroying the experiment every time. We don't quite have an experimental platform like that. But that could be, but the cracks will be affected dramatically. Okay, so I promised one thing, and now it's time to start delivering it. I said I was gonna show you how the spectrum is changed. First in the dishonest way, and then in the honest one. So let's start with the dishonest way. So what's the essence of that approach? The essence of that approach is the following observation. I mean, when something is difficult, the only way to understand it, I think, is to see whether you can reduce it to a dominant balance of two things. Maybe three, if you're lucky. But two is better. Two things that fight against each other that compete. And then the answer you're seeking is the balance between the two. Okay? So here, let's say that what I want to understand is the following. Nikta's experiment, unlike these guys that you saw, are small. What does small means? I don't remember. But scales were the so-called Reynolds number. Do you guys know what a Reynolds number is? Like, you see, like the thing that you have to understand is the dynamics inertial or dissipative, right? Do you have two derivatives in front of the displacement or one? Okay. And the answer to which of these two effects matters depends on the size of the object. It's very difficult, maybe impossible, to have inertial dynamics. Okay? So when Nikta says that she's measuring waves, one has to understand a bit what type of waves are this, because you have an overdamped system, and yet stuff propagates. So how does that work? So the idea is the following: is the same reason why the guy that was coming up can climb. You use the work cycle to overcome dissipation. So the amount you can, in the same way as the speed that guy climbs depends on the odd elastic coefficient, similarly, the speed at which the wave moves will depend on the odd elastic coefficient, because that guy tells you how much work I can generate per unit time, and that tells me how much I can dissipate per unit time if I balance the two. So if I want to extract in a dishonest way what's the name? Maybe not quite the spectrum, but the dispersion relationship of this wave, that is not going to be omega equals ck. That is the answer that you have generically for acoustics. I have to balance the energy gained in the loop to the energy being dissipated. And if I can do this estimate and balance these two things, maybe I can get the dispersion relationship without doing any calculation, just based on dimensional analysis. This is what I'm going to try to do. Okay. So where do we do it? Maybe down here, up here. So what we're going to assume is that there is a medium, and in this medium, there is a solitary particle. This particle gets deformed and moves up here, let's say. And then during the passage of the wave, it has an amplitude. This amplitude is going to be called R. Okay. Now, the first thing that I want to do is I want to get the work done in the cycles that will be induced by this wave. So remember, the work done is equal to W. Actually equal, let's just do this, proportional to an elastic coefficient, let's call it K naught, but it could be A, depending on what type of wave you excite. So an odd elastic coefficient times what? The area in strain space. So what is an area? What is strained by dimensional analysis? Displacement is length. R. But then you have to take the gradient. So the length over which the R will change depends on the wavelength of the mode. So if I want to get a measure of strain, I take R and I multiply by Q, where Q is the inverse wavelength of the wave. Is the logic clear? But this is not an area in strain space. This is just strain. What do I need to do? Square it. So this is my budget. Okay. Now I have to invest it to overcome dissipation. So I have to make a poor man estimate to dissipation. Poor man estimate to dissipation is, let's say that there is a coefficient that I call gamma. Gamma times velocity squared is the rate at which I'm dissipating things, right? And if I multiply by time, that's the total dissipated thing. So the time that matters here is the period, which is the inverse frequency of the wave. Let's call it T. So I'm going to say energy, work done, energy dissipated equal. So dissipation coefficient gamma, okay? And then I have to write down the displacement field of the particle U dot velocity squared times the period T. Do you agree? Yeah. So this object here, well, U is R because it's the displacement. Do you agree? So R squared divided by T squared, but there's a T here. So all you'll be left with is gamma R squared times T, correct? No, 1 over T. You see why? Because there's T squared here. But 1 over T is omega. Okay? Yes? Can you guys follow this? If you don't follow, I didn't explain it properly. Huh? Gamma is a coefficient of dissipation that I just put in by hand. The dissipation coefficient, drag, whatever you're going to call it. You know, like if you drop a ball in water, it dissipates, and there's what is called Stokes drag, something like that, right? So if you don't like gamma, call it with another name. But you need a coefficient for dissipation. So now I have to balance this thing here with this thing here. Okay? And I'm not claiming that there's nothing else. I'm just saying these are the two dominant things that I have to balance. So look at this too. Why do you look at it? Yes, because R squared cancels. So this amplitude it's irrelevant because we're going to try to do linear waves. That's the reason why it cancels. And then you get omega equal, well, equal is too optimistic, proportional to K naught Q squared, kind of interesting, divided by gamma. The larger K naught, the higher the frequency, you divide it by gamma. Notice this dispersion relation is Q squared. It's not CQ. This is a dispersive wave. Okay? It's even a bit more than that, is direction. So it's magnitude QQ, okay? But at the level of scaling is Q squared. So now imagine, if you can measure a spectrum of the waves, which NICTA could, then by fitting the lowest part of that spectrum and knowing what the dissipation coefficient is, you can extract something like K naught. Okay? Now, what I want to do is I want to show you the honest way of calculating these things. Because the honest way, this is just an estimate. Leo. Huh? But this is real. This is real. This is a propagating wave. Now, this question, though, is an excellent entry to what I'm going to do now. This is an estimate, assuming that this wave is moving, it's propagating, but presumably there is a calculation that says, given that you have now presumably understood the elasticity, write down the equation of odd elastodynamics, calculate the spectrum, calculate what this omega is with the real and imaginary part, and out of that calculation you will have presumably these results somewhere, but also the domain of stability of these waves. You will also be able to understand the onset of these traveling patterns and the mathematical condition that dictate it. And this is what I want to do now. Okay? And you will see the imaginary part coming up. So now, to do the calculation, I'm going to continue here. What I want to do for a moment, I want to say, look, you see that I'm a big lover of this geometric and pictorial language, but I just want to expose you at least to the notion that there is a different way to represent all of these things using tensors. And the other thing is that the rest of the world uses it. So in the lecture notes that I've given you, there is a translation dictionary between this pictorial language that, in my opinion, allows a lot of insight at the qualitative level and all products of epsilon and deltas. So if you wanted to write down KIJMN, not using this pictorial notation, but a bunch of delta and epsilon, this is how it would look like. The bulk modulus will look like delta IJ delta MN. The shear modulus, and sorry, this formulas can be written knowing how we wrote the other one, because it's essentially those tau matrices that contain the delta and the epsilon. I'm just now writing them with names. So the mu, it's delta IN delta JM. You see, my problem with this is that I die of boredom even when I write it. Huh? Well, but when they yes, it's true. That proves that maybe that love is limited. Okay, yeah. And then there's a K naught that multiplies an object that I'm going to call EIJMN. And there's an A that multiplies an object that's called delta MN. Notice that the A comes with the epsilon IJ because it's the torque. Okay? So this is the tensor. I have to tell you what this E is. This E is another monster, EIJMN equal 1/2. And you can check that all of these terms are the only one that you can write with all the transformation property that you want, incidentally. So people that are pros at this game, they would just write it down by inspection, essentially. Can you see this? Where is it? This one here? I don't have it. Big, yes, yeah. So you dimension, so it would be 1/d. It would be one of. Let me not put it and then get back to it. I have to check that it has all the symmetry transformation. Okay, once you have this object, what do you do with it? Assuming that you wrote it down correctly. You have to write down an equation of motion. Okay, so let's go here. We'll have to get rid of our beautiful notation here. Okay, now you write rho dt squared uj plus gamma dt uj. This is the drag. This is the inertia that we're gonna throw away for Nick's experiment, but it's important for current dance one. And then on this is Fj. But what is Fj? Fj is the divergence of the stress tensor. Okay, so let's write it down. It's going to be di sigma ji. Okay, now sigma ji is kjimn times the other one. So this thing will look like kjimn di dmun. Okay. So the bottom line here is that notice one thing: the strain had already one derivative of one. When you take the divergence of the stress to get the force, you pick up two derivatives. So all of these terms originating from this formula will involve two derivatives, multiplied by some curl, whatever it is, but all of them will have two derivatives. Okay? So now what you do, for our purposes, I'm going to drop this. Purposes, let's say. And then I have to take the formula that I'm doing something not correct. No, this formula, stick it in here, do all the contractions, assuming that I've done them correctly, and I'm going to get the following. This equal, so this equal B dj, maybe we can write it already. Yeah, sorry. dj divergence of u, okay, which maybe I could write a grad divergence of u, plus mu Laplacian for uj. So maybe let me do it consistently by writing the divergence of u as di ui. Okay, so that here you can see all the. Then there will be a epsilon jk dk di ui plus k naught epsilon jk Laplacian or uk. Okay. So can you see what I've done? So now one thing I want to show you is that let's do a simple, just to get a quick sense of where we're going to go. Let's say for a moment that we go in this limit, where k naught is much larger than all the other coefficients. So potentially, we could be talking about a medium that has zero normal moduli, conserves angular momentum, but it does have an odd moduli. And it's overdamped. So if you thought of it from the perspective of normal elasticity, you say this medium is overdamped, so there cannot be kinetic energy. The moduli are zero, so there cannot be potential energy stored. How on earth are you going to get the oscillation characteristic of a sound wave if you don't have the two components of that? Well, the answer is our heuristic argument indicates that that comes from the balance between two different things: power generated and dissipation. And those two terms are still there. Okay? But let's see that coming out mathematically. And more precisely, what you see is that there's a symplectic structure that emerges in the problem, right? Like an harmonic oscillator written in Hamilton, using Hamilton equation. Well, let me show it to you one more. So what I'm going to do is this. Let's say there's two dimensions. So this guy has two components, and it's going to be in matrix notation u dot x, u dot y, agreed, equal. Now, if all of this, and this, I can drop it, I'm only left with this. Agreed? This is Laplacian of this guy multiplied by the antisymmetric matrix. So this thing looks like K naught, 0 minus 1, 1, 0, Laplacian of ux, Laplacian of uy. Can you see that? Can you see that? And if you do a round of Fourier transform, you just get rid of this guy, you pick up a q squared in front. Okay? But now, is this structure, a bunch of things with a dot multiplied by a matrix that's antisymmetric times the same thing familiar to you? I would argue that if you write down Hamilton equation for an harmonic oscillator, and instead of ux and ui, you have x and p, that is to say a coordinate and a generalized momenta, it has that form. Okay? So here you can already see the oscillation that is emerging. And the k naught divided by gamma that is coming for free in front. Okay? But that is only in this limit. Whereas I want to work in the limit in which I have also the rest. Why? Because you see, for this wave that is powered by odd elasticity, the normal elasticity will be a hindrance. Because the odd elasticity wants to make it go in some path, but that path may entail compressing whatever it is the distances. So there could be an attenuation due to the normal elasticity. Okay? And if I want the full answer what the spectrum is and the stability, I just shouldn't do all of this. But here you can already see the estimate that I did, it's essentially this calculation. Okay? Let me continue it so it's even more apparent. What do I need to do now? Well, if I want a spectrum, I have to put an ansatz for the solution, which is an oscillatory ansatz. So I'm going to say uix is going to be equal to uiq times e to the I q dot x minus omega t. Okay, this is what you would be doing always, right? Now, if you take this and you substitute it in here, you get minus I omega tau uj hat, which is this guy, equal minus qi minus qm, and let's say ki jmn un hat. But if you plug in the choice for this object, the final expression that you get is simply q squared. Sorry, I want to do one more thing. I want to simplify my life. I want to introduce longitudinal and transverse component of u. In particular, I'm going to introduce a variable that I call u parallel, which is qi at ui tilde, and u perpendicular, that is epsilon ij qi uj. Okay, so essentially this is the projection along the longitudinal and transverse direction. Yeah. How I got what? This one here? Yes, absolutely. So under this condition, I can set this term, and this term to 0 because they're much smaller than k naught. Then this epsilon jk is precisely the antisymmetric matrix in 2 dimensions. And then the Laplacian of uk is written as Laplacian of ux and Laplacian of ui. Okay. So with this language, this equation can be written as minus I omega gamma u parallel u perpendicular equal minus q squared b plus mu minus k naught minus a mu k naught And here I need to steal a bit from this blackboard. Okay. This equation here is the spectrum, but it's still not in a particularly again. For K, I'm JMN. In this expression, I'm using the full K naught. In fact, notice that there's K naught, there's A, there's B, there's mu, there's all of them in there. So this is true for any choice of parameter. Okay. So here I've used the full one from above. Okay. So now we have this object. This object is still not what we would like to have. What we would like to do is the normal modes or the eigenvalues of this system. But again, you can just solve it. It's a 2x2 thing, so you put it in mathematical, you do it by hand. And the answer you're going to get is omega equal minus I. So this comes from diagonalizing that matrix. Beta divided by 2 plus mu plus minus square root of beta over 2 squared minus K naught A minus K naught squared. All of this times Q squared. Now, I would have loved a bit more space. Let me try to squeeze it. Minus K naught A minus K naught squared times Q squared over gamma. You can see that the honest way is much more painful than the dishonest one. Notice here, we start seeing appearing the Q squared over gamma features of that dispersion. But there's a bunch of interesting things here, right? And so the first thing that we can notice is this thing, this piece here, is multiplying an imaginary component that you were asking before. So the bulk modulus and the shear modulus are acting as an attenuating factor for this wave. So it's the other way around as a normal sound wave, okay? Because K naught forces a deformation, this guy resists. What else? So let me write down the decay. The second thing that is quite interesting is that there is evidently a condition for the onset of this wave. Okay, and that is actually something that I want to analyze in detail. What is the onset of these traveling patterns? Because it will take us to a concept called exceptional points. It is very important in this to understand both response function like odd elasticity, but also non-reciprocal phase transition. So the onset, in principle, is very simple to calculate. The onset of this propagation occurs when e to the I, e to the plus minus I real of omega t. So you want essentially this thing, you want omega to acquire a real part. Can you see what I'm doing? No? So let me. This is it's complex. This object is complex. So if I put it into e to the I omega, it will give decay. If I want propagation, it has to be real. The weird thing is that so in order to acquire a real part, it's all a bit weird because there's this eye here, which is a pain in the neck. But for this to be real, this guy has to be imaginary so that he cancels the eyes outside. That's all I wanted to say. So it's a condition of this, what is it called? The integrand. Yeah, the thing that is inside the square root is got to be negative. Clear?
Low activity.
Yeah, it makes an eminent sense. So let's write it down though. So what I propose to do is you take the beta out and you write this object here, beta b over 2 times square root of 1 minus k naught tilde a tilde minus k naught tilde. And you define as k naught tilde and a tilde the ratio of a and k naught divided by b. It's just convenient. So a tilde is normal a divided by bulk modulus. And this quantity, you want it, in particular, this quantity under here, you want it to be less than 0. Okay? So that tells you that there's a condition a tilde equal 1 over k naught tilde minus k naught tilde, which is a boundary in the space of a and k naught, where you will start seeing a wave. Okay? So let's try to recap what we're trying to do. We're trying to say, given an elastic medium of values, odd values a and k naught and the other stuff, in what range of these parameters our wave allows to propagate? And then we make a phase diagram. And then, since we have a calibrated microscopic theory that in terms of those parameters tells us what a and k naught are, we can draw a line to see where we are. And that's what we're going to do. Okay, so this corresponds to the condition in which this integrand is strictly 0. Clear? This condition is the boundary for active waves propagation. And the condition as an inequality is that this integrand is less than 0. Let me box it. Okay?
So when k0 is 0, you don't have any track. Right?
Yeah.
Is that generally true? Like two-dimensional crystal you never have?
If your crystal is overdamped and you don't have odd elasticity, there's no traveling waves. I mean, they can be for a transient, but not steady state. Absolutely. So I was saying, it's doubly troubling. Here, you have overdamped and no elastic moduli, and you have wave propagation. That's why it's peculiar, because you would never have that.
Normal crystal, you have to keep the road.
Yeah. If you had only normal moduli, you would have to keep the absolute. I should have said that. If you don't want it to decay.
Have the sound plus the width. You have some decay, but decay would square.
Yeah.
While the propagation.
It would be linear in Q. That's the point. So a small Q, long wavelength, that will dominate, which means that you will observe it for a while, and then it will go down. Yeah. Yeah.
Guaranteed.
Underdamped.
Wow.
Whereas overdamped is the opposite regime. Okay? Good. Now, there's one more thing, though, that we need to figure out. This is the condition for the onset of the waves. But you can imagine if I start cranking up this k naught really large, maybe despite the dissipation is there, stable. In Corentin example, there we use the underdamped dynamics. So it's even easier to create instability. But you could ask, even given that the dynamics is overdamped, is it possible that when k naught gets sufficiently strong, this wave will become unstable? So how do we answer that question? Anybody is still analyzing this object. If the spectrum, that is this thing, acquires a positive imaginary branch, then when you put that inside the exponential, it will be a runaway solution. So what is the condition for that to happen? Well, let's look at it. And this will be the last piece of algebra. You want to take beta over 2 plus mu plus min, well, you can concentrate on the minus, beta over 2 squared minus k naught a minus k naught squared. You want this thing to be less than 0. Okay? Okay? But you remember this, the various signs there. Now,
But it's a bit basic, but could you like quickly go over the difference between like omega positive, negative, real, imaginary,
Yeah.
like all these four
Yeah.
quadrants, what do they mean
Yeah.
physically?
so whether omega is positive or negative, that's clockwise, counterclockwise. In front, because we'll tell you whether you have decay or you have growth. So if you want to avoid the instability, for example, let's look at the first beta over b over 2 plus mu is multiplying minus I. Okay? So the moment in which you put it inside there, EIQX minus omega t, there is an I and an I that gives you a minus, but then the plus cancels, so that gives you decay. But if that thing was positive, it would give you a growth. And that would correspond to this condition. Okay? So this is a condition for instability because of the growth. And these conditions, once you do the same convention as that, can be written as minus 2 mu star plus mu tilde squared plus k naught tilde squared divided by k naught tilde equal a tilde. So this equation in the space of k naught and a tilde gives you the boundary of the zone that is that separates stability from instability. Okay, and if I try to plot these things, tilde, mu tilde is the shear modulus divided by the bulk modulus. So any tilde variable is the original variable divided by the bulk modulus. I wrote it only for one here, but you can, it's the same thing for all the others. Okay, so actually, is there a chance that I can raise, well, actually, I can probably move here. So what I can do now, I can actually make a plot that you guys find in your lecture notes, which is a stability plot that I advertised before. And what this has is, it's a plot that on this axis has 2k naught over b. This is what we call k naught tilde. And on this axis has 2a, there's the stupid 2a, 2 that keeps running, but that doesn't matter. This is a tilde. Okay. And now in this space, I can draw this curve and this curve. And these are the two boundaries between wave propagation instabilities. And I'm going to do it for you. So this curve here looks a bit like, I'll do my best to draw it, and then you can do it with Mathematica yourself. Okay. And these two lines are obtained from plotting this. Zero, yeah. And then using this other condition, you can plot another line that is here and roughly here. So this region is unstable. So is this. that means that your moduli are sufficiently high that do not allow propagation of waves. Here, what this means is that here there are active waves, but inside here, there's no active waves because the moduli are not large enough to allow the propagation of the waves. So if you like, here is the domain of active waves. By active waves, I mean these waves powered by K naught. Is this clear?
I guess we need like
Nonlinear term and blah, blah, blah. Yeah.
That actually looks like in the material.
Yeah, it's not entirely clear. Simulations in that regime indicate a real instability, meaning you see it moving chaotically. It probably depends on what type of what I'm saying with simulation. Although that is the outspring that we try. Not perfectly clear. Not perfectly clear. I have a comment actually for everybody, but especially for you. Notice. Here, there's a I omega q squared. What type of equation, fundamental equation of mathematical physics, has that dispersion relation? Yeah, diffusion. Why do we get diffusion? What's diffusion? Diffusion for me is continuity equation. There's some, is it called continuity equation, yeah? So what is the conserved quantity? Here, linear momentum. So if one added nonlinear terms here, this would be an example of what people call model B critical dynamics. So there's an order parameter, there's a conservation law associated with it. There are others that are simpler, but this is one of them, okay? For our purposes, this is the signature of a conservation law, okay? Which in our case is linear momentum. There's another thing that I want to, another nomenclature, another thing I want to emphasize. Notice that, so this is the zero shear modulus, zero A, zero K naught point, okay? Once we have a microscopic model like the outspring, we can coarse grain that and find expression for K naught and A. This is what Nikta uses, okay, from Lara's paper. Then, essentially, there's a curve of Ka divided by K. You remember Ka was the microscopic coefficient, right? And you know how A depends on this, and K naught depends on this ratio. So you can draw a line here. Okay. This line, it's a line of increasing Ka over K. And when that line hits this point, you know that your microscopic coefficient is large enough to allow wave propagation. See what I'm doing? I've drawn this locus. Okay. So one question that you can ask is, what happens along this line physically? What's special about it? What's the condition for this wave to propagate in general terms? And this is a key idea in what people sometimes call non-Hermitian mechanics. So it's a bit of a mouthful, but one aspect that I want to emphasize is that the dynamical matrix of the system, Andrea and Doug were talking a lot about dynamical matrices, right? And the dynamical matrices of those systems are Hermitian matrices. Like the mechanics. So people who study quantum mechanics of open system, or more simply, system like the one we're describing, they have to deal with this non-Hermitian matrix. The root cause of this non-Hermiticity is the fact that these interactions are non-symmetric. If you go back, for example, look at this equation. All our equations have off-diagonal terms that are not equal, which means that there is a non-reciprocal interaction for these two components. Reciprocal means non-symmetric. Okay? Whenever you have that, you generically get this type of subtleties. Now, notice that one of the consequences of this fact is that the eigenvalues, the eigenvectors of these matrices are not guaranteed to be. Now, I will write it. For this system, you can, actually, I'll leave it to you as an exercise. For this matrix, you can write the eigenvectors. And the condition that happens at when you cross from to here is that the eigenvectors that were not guaranteed to be orthogonal, as you move towards that point, at some point become collinear. They coalesce. This condition is called an exceptional point. Above it, there's the propagation of waves. Okay? So the propagation of these waves is mediated by this object called exceptional point. How are they obtained? You get the dynamical matrix, you find the eigenvectors. When they coalesce, that's the exceptional point. Bang, there's the propagation. Okay? Yeah, is the condition. Okay? And so, armed with a diagram like that, you can essentially predict the behavior of the system, stability, wave propagation. And once you start seeing the waves propagating, you can recover also that result that we had before in the limit in which K0 is much larger than all of the other quantities. This diagram is for, actually, mu drops out. Or rather, yeah, it's for a fixed value of mu, and then you only keep track of K0, and sorry. Because it's implicit in, where is it? It's implicit in this mu. So in order to the only thing that is interesting, that maybe that's what I said dropped out, that this guy did not depend on mu. It's only the stability one that did. So the whole diagram does depend on mu, but some features are not.
Reactive waves require to have like positive imaginary part with precipitation, but don't we also have to require to have enough like non-stability in the amplitude? Because otherwise it would relax fast.
Yeah. So this is a linear stability thing. The amplitude dropped out. But the point is that you don't want something. I see. What you want to know is what happens really here between these two. I don't think, I think the question, if I understand correctly, is that this diagram, at least as is drawn, I mean, it may be continued. The question is that if, why don't I see this? Why doesn't this blue, if I understand correctly, why doesn't this blue region intercept this? So I could potentially say that as I come here, I have an active wave. Then if I increment it up, it will go unstable, as opposed to go from no waves to instability. I don't have an intuitive answer. I don't know what my memory is that this don't cross even when I continue it, but I don't have a clear answer to that. Please notice that the condition for the propagation of the waves are not necessarily tied up to the existence of the instability, because the condition for the propagation of the waves is for the energy to be channeled in a certain way. So, your intuition that the instability should occur when the wave grows too much, that's not guaranteed a priori, because the instability occurs when you pump too much energy in it. And it's not clear that there should be a precursor that is a wave.
You only have a wave when you discriminate with negative.
Yeah.
But then now you have no damping. no way to reduce damping.
Right.
When discriminant is real
Yes.
or positive, the square root is real.
That's the condition for the wave.
Growing, but once it goes, it only oscillates. There's no, you no longer, you can never.
But why does, but okay, but this thing here, this, yeah,
Either it's imaginary, the square root, then you have oscillations, and now you don't have plus damping. You never have amplification. You never have amplification and oscillation at the same time.
yeah. Yeah, but if I look at this here, which is my condition for going unstable here, I can totally write it down. So I didn't understand. Are you arguing that there should be what? Oh yeah, sure. But the question, so yours is a sort of mathematical answer. I thought that the question was, how do I what's the, the intuition there was, I think, physically, why can't I say generate a wave and then pump energy in that wave so much that at some point it goes unstable? Now, it doesn't have to be like that. If I even give you, recapitulated that calculation, how it works, there's one thing that I have to argue. If I wanted to know what happens in a linear wave when I start loading energy more and more, I would not truncate things to the linear level. Here, I've killed all the nonlinear terms. My feeling is that to answer that question, I need to restore the nonlinear terms and see what happens with them. Otherwise, I'm inherently confined in this analysis by linear stability. And within that linear stability, this is what happens. I wish I had a better intuitive explanation, but I can only argue mathematically. Yeah. Yeah. Well, okay, good. So we wrote papers on this. How do you see from the equation? Well, so there are two types of topological modes that this thing sustains. One is called a skin mode, and another is called it's sort of standard chiral edge mode. The general conditions for having chiral edge modes is you need something like a magnetic field or a chiral term. Odd elasticity is such a thing because the epsilon, I'll show you. Let's look at the equation. Something like this. It's a little bit like a Magnus force, right? With electrons, you have B cross V, for example, or Coriolis force. These are the typical way of inducing topological edge mode. This guy is a similar thing, but with a Q squared factor in front. So it breaks time reversal symmetry, so it has that criteria. The only thing that there is not clear from looking at that equation is that you don't have a gap. However, if you want to use odd elasticity to create chiral edge modes a la Haldane, for those who know what that is, you have to create a mechanism for gapping them. One of them is to make a thick thing, like a membrane. Then the thickness of the membrane gaps some of the modes, and then the odd elasticity gets them to become chiral. And there is a paper that we wrote with a visiting undergraduate student called Michele Fossati that is called chiral edge modes in plates with odd elasticity. And what I'm talking about is the recapitulation of that. I apologize for those who don't know what these things are, but it's hard to explain it in all details. Sure, with pleasure. Yeah, thank you.